Okay, so welcome to the last session of this first week. So I have an announcement to make. As you know, yesterday we have this poster session. A professor was in charge of selecting the best poster, and we already have a winner, which we want to congratulate. And the winner is Jamile. Please stand up. Okay. So hers was the best poster, and she will receive a prize. However, what this prize is won't be announced until next week. Yes, because there will be another prize for the second poster session. It will be the same prize. But congratulations, Jamil. Okay. Okay, so today our final talk then will be by Antonio Santos, who is going to tell us about Anapole dark matter. Please.
Okay, thank you very much. Thank you. Thanks for the organizers to let me give this talk. So in this work, we gonna analyze the potential of discovery of Majorana fermions as a dark matter candidate interacting only through an Anapole moment. So this will be probed in the LHC. So I will give some introduction about the LHC, how we can analyze and classify events with dark matter, and I will show how to use machine learning tool to classify events, and I will show my results and conclusions. Okay, so just to a brief introduction. Oh. So this is our dark matter candidate, Majorana fermion, that interacts with a photon through this interaction called Anapole. And we're gonna analyze it in the LHC through a monozet channel, which decays into leptons. So this analysis will be done in the LHC. The LHC accelerates protons until velocity is close by the velocity of the light, and it generates a very collimated beams in such a way that we can consider almost no distribution of momentum or energy in the transverse plane. Once a particle is measured, we can measure some observables related. And with that, putting it in the same ideas in what they use in data analysis, this is what we call the low-level features, is the most fundamental ones. But you can do combination of these features, and for instance, create angular distance, the invariant mass, and the combination of those variables can give you a more clear idea about, for instance, what was the event related with the final states measured particles. And for this example here, we have, for instance, characteristic peak related with the the production of the Z boson. Okay, and add that just to remember, since you have very collimated beams, you can use the energy conservation to build what we call missing energy. Same for the momentum conservation, and with that we can characterize, for instance, better dark matter events, because as we know, dark matter will not give you any signal in the LHC detectors. So after, in this analysis, you identify a particle, how you, based on these particles, how you classify the original event. So we can think with this example here, you represent your physical process through some observables. In this case, we are giving this example when you are trying to classify these blue dots over the red ones. So based on these variables, you can think about a boundary decision, which determine what is inside of it, if it's a signal event or a background. You can use the cuts, and it creates this characteristic rectangular shape. You can use linear models or non-linear models to classify them. So in this work, we employ boosted decision trees to perform this surface, determine what is the best surface to classify these events. The boosted decision trees is composed by nodes and leaves. And in particular, we use this XG boost because there was in 2012 called Kaggle challenge, and this was one of the best algorithm to perform classification with Higgs events. Okay, and the name is boosted because it uses a combination of trees in order to give you better results. Okay, so this combination of trees can be seen as classifiers functions, related with your observables, and at the end it will give you some classification. And the objective of these trees is to minimize some error function and minimize as well the complexity of your model. I mean, if you have your data, you can have a very bad model, but if you construct a super specific model, you can fit your data once, but in next bunch of data, this model can give you worse results. This is what they call overfitting, and this is the one underfitting. So this, of course, depends on the number of leaves, for instance, and have some parameters that you need to turn during the process. That you have a algorithm to check if you allow a leaf to become a node and you create new leaves. And this is with respect, of course, of the results with just the previous leaf. And you have another parameters if you don't want to, if this new branch is not good enough, you can cut this division. Okay, the tree is a composition of weights. This weight is calculated by the number of signals and background events that follows in each leaf. And as I told you before, the model is composed by a combination of trees, but we know that the first tree has the most power in classification, so the next trees is added just to give you secondary classification to increase your first result. So the next trees we multiply by a weight less than 1. This is called the learning rate. So boosted decision trees has some parameters that you need to turn in order to optimize your results. But so usual way to turn these parameters is by a step-fixed search. But there are some papers that shows empirically that random search gives you a better look about the power of your parameters. But why you are using a machine learning tool? Why not use a machine learning tool to improve these results? So you can, the idea is change all those parameters in just one using this hyperauth algorithm. So the idea of the algorithm is, okay, during a random search, previous results do not give you some ideas about the next step, okay? Sorry, the best result that you get from the previous results do not help you to think about how to improve the combination of the parameter search. So this algorithm, we will use the previous results and we'll give a slide, very small weights in the combination that of among the parameters that gives you the best results. So it creates some distribution function over the parameters that gives you better results. And this is the main idea. In a random search, previous results do not help you with next iterations, but the hyperop, you slightly, for instance, in a uniform random number, they will change a bit for a Gaussian distribution. And as you can see, to avoid the local minima, it has some random nature until the end. So in this analysis, we use the M log loss in order to capture the misclassifying in the boosted decision trees. And for hyperopt, it will optimize the parameters in the boosted decision trees, looking for the highest statistical significance. This is a function that takes into account the number of signals and the backgrounds in order to really achieve discovery. This is the syndactic formula approximative. Okay, but this is a kind of supervised learning. So in the beginning, you need to show to the algorithm what is your signal, what is your background. And simulation in the LHC is composed by the hard interaction. After that, during this hard interaction, is produced a lot of QCD radiation, for instance. You need to take it into account. Add that you, of course, can have a lot of different amplitudes that contribute to your final state. To do that, we used the MedGraph. Okay, and parton shower, this radiation, we know in low energy levels that this is not measured. You have the hadronization. To do that, we employ the Peter. And you need to take into account the detector effects. In this analysis, we use very common in particle physics phenomenology to use the Delphi simulations, Delphi package. So to do all this analysis, we implemented the model in fine rules. We generate the events in MedGraph at parton level. We employ the PTIA for parton shower and hadronization, detector simulation with Delphis, and data analysis. We extract our simulated data with Fortran codes and employs the boosted decision tree, which is written in Python or C++, but in particular we use Python version. So this was our main channel, this Anapole through the leptonic final state. And we analyze the power of the, if the LHC can probe this interaction, right? Okay, this Anapole interaction, we have a classical version of it. Looking at the Hamiltonian, we have the magnetic moment, the electrical dipole moment, and we have the Anapole part, and we have a similar in the electromagnetism. And we have analogous in the quantum field. This is, for example, in the minimal supersymmetric model where we have the neutralinos interact with the S particles, and by loop induced, we can have this Anapole interaction. Okay, the first work considering dark matter as interacting only through the Anapole interaction was made in 2012, when they calculate the Rayleigh abundance for this interaction here. And in this analysis, again, we analyze the potential of discovery in the LHC through the mono-Z signal in these leptonic channels. In this case, we have these are the irreducive backgrounds and the reductive ones. This is classified like this because this background do not generate the exactly final state as we are studying, but for instance, this lepton here can be too soft and misclassified as a missing energy, for instance. So at the end, you will have the same final state. So at that, we applied some trigger cuts, and are the cross sections. The number of expected events is the luminosity, integrated luminosity, times the cross section, and the efficiency of the cuts. Worth to mention that, for instance, we have, you can look at this, for instance, the tau and anti-tau, top anti-top background. You can see here it has a huge cross section. On the other hand, after cuts, you can almost exclude it. For instance, based on this jet particle in the final state. Other good way to classify this event, for instance, is because this final state do not generate a lot of missing energy in the final state. So you can put a cut and almost exclude it. So these are the kinematical distributions of in this. Here we have the signal and the continuous line in the background. Worth to mention again, is worth to mention that the number of expected events is multiplied by the cross section. So here this plot is normalized to 1. So normally the behavior that you expect is something, for instance, in this distribution of the angular distribution of these two leptons, you have for the background something like this, and the signal will be much over the number of expected events for the backgrounds, as I shown here. You can see that the cross section of the signal is much smaller than the backgrounds. Okay, so we employ the hybrid analysis combination with some small cuts in the beginning, and it's important to mention that if you cut a lot in this first step, just a few of events will left to train the boosted decision trees. So the boosted decision trees don't learn a lot, so your results became worst. And this is the way we are representing our data. Okay, so what the boosted decision trees do is it converts all this information into a new distribution, but in this case, the number of events from this signal is more related with this distribution in a way that if you indeed put a cut here and accept just events related with some, for instance, value higher than some threshold in this variable score, now you have indeed more signal events over the background ones. Okay, so it's common to analyze the performance of the boosted decision trees to use the Roc curve, which relates the signal efficiency of the how you maintain the signal events over the rejection of the background events. So if you are interested in maintain more event of the signal, unfortunately, you can maintain more background events as well. Other important part here is what they call feature importance. It's important to mention that the feature importance for the boosted decision trees, at least in this XGBoost algorithm, they count the number of times that some variables appears in during a split in the leaf to become a node. So sometimes, for instance, some variable is used just once, but this variable can have a huge power of classification. But after some cut, it loses power if we employ it again. So in this case here, even if some variables appears over and over again, this doesn't mean that this is really important. This is the reason why if you exclude these not so important variables, the results got worse. And this is the physical part of the analysis. The cutoff energy that the LHC can probe in relation with this score variable here. You could think that, okay, I can put a cut here and I can probe a lot of new physics, but we see that for that region in particular, the algorithm, since you have less event from the signal and background, you have some fluctuation due to the systematic uncertainties. So you need to, in this work, we selected this variable, this cut in 0.95, and our results just changed about the 10%. Okay, other metric which is very common in data analysis is the confusion matrix, which relates the predicted label by the boosted decision trees with respect with the true label. In this case, worth to mention that we simulated mass for the dark matter mass for different values, 100 until the 500 GeV. And as we can see, in the case of the 100 GeV, the signal is more similar than the backgrounds. In the case, for instance, the ZZ event. And this is our results considering different level of systematic uncertainties. Okay, since this is a search in the collider physics, we interact with quarks. In this way, the direct detection is a good constraint as well, and we perform this parallel analysis to compare them. So, but there is a problem here because, as pointed out, the collaborations gives just a type of interaction, which is the contact interaction, but it is different from the Anapole one in such a way that, for instance, in the case of contact interaction, we have this differential cross-section, but in the case of Anapole, we have, at least these two terms. As you can see, there is a velocity dependency here, similar for this term. On the other hand, you have a new term, which don't have the same relations. So this will give a different rate against these two different approach. So you can't use directly these bounds here. You need to do some you need to high scale. So this is our results compared. This analysis was done in the end of 2017. In that time, the best result was the Lux one, but we compare with the projected results for the Lux Zeppelin experiment. But this will happen just 10 years, if I remember correct, just in the next 10 years. We compare as well with a simplified model, which where the dark matter interacts to a S fermion with the fermions of the standard model. We have some mixing between the S fermions, and the amplitude that contributes for the Anapole interaction is this one, and this is the loop interaction that generates the Anapole interaction. Here we have some analysis of the behavior of this Anapole interaction. Okay, and this is our final results. Just remember, we were considering the luminosity of the LHC through the 3AB inverse. Okay, and just to add, this blind spot here can be measured with the indirect detections. Okay. So the conclusion is we perform analysis about the potential of discovery of this Anapole interaction in the LHC. We compare with some simplified model, and it's important to mention that even if in a future direct detection experiment could detect this kind of dark matter interacting to this Anapole moment, it's important to mention that you need to have sign-off with all different kind of experiments. So the LHC can play a parallel job to do that. And just to mention that the collaboration in the LHC Atlas, always when they use these new tools of machine learning, they found some improvement in the previous analysis. And maybe we can, inspired by the Gelmini talks, maybe we can scatter eventually with this transparent matter. So this is the end.
Questions?
Maybe I misunderstood something, but I'm not sure I understand what you do for the simulation of the signal. In the sense that if I understood your operator, you have an effective